Hi, I'm Dr. Bear, and I'm going to give you a demonstration of a numerical model that I have for a quantum harmonic oscillator. This model is available to you on GitHub freely. There's a GUI, or a graphical user interface, involved here, and this tutorial is all about showing you how to use that. Once you download the code, if you look for any files ending in fig, there it is, you'll see there's the name of the GUI itself, Dissipative QHO tool, so Dissipative Quantum Harmonic Oscillator. And you have to do this in MATLAB, so if you type the name and just hit enter, it brings up the GUI. In the upper left, I have n, the size of the truncated basis in which we're modeling this quantum harmonic oscillator. And the basis states are the eigenstates of the quantum harmonic oscillator. Here's the oscillation frequency for the harmonic oscillator and the effective mass of the harmonic oscillator. We're going to do a time simulation for this many oscillation periods, and each period is going to have 75 time samples in it here. You can choose the initial state, so you can choose the ground state, first excited state, so on. You can see here that we have the ground state. This is the initial state here. And then you can actually add environmental coupling. So right now the oscillator is disconnected from the environment. We can add energy dissipation or dephasing, or both together, thermalization. So let's just go with none for now. Here's a status window that tells us that the time evolution was just calculated in 29 milliseconds. And then here's some data. It just tells me what m omega squared is. Up here is a multi-purpose figure. So I have potential. You can see here, this is the parabolic potential. These purple lines are the eigenenergies. I can also look at position, the probability distribution in position, and time here. So time on the x-axis, position on the y-axis. Time here is scaled in tau, which is the vibrational period. Another option, entropy. It's a closed system. It has zero entropy. And then the expectation value of energy, again, closed system. Starts in the ground state, stays there, constant energy. There's an animate button here. So we're going to see 180 movie frames. There are actually 450 time steps. If I hit animate, well, this one's very boring because we're looking at a stationary state, and the probability distribution down here is not changing in time. So this is the instantaneous probability distribution, and this is the instantaneous distribution in Fock space, or in the eigenenergy basis. So let's look at a more interesting state. I particularly like the coherent states. So here's a coherent state. You can see here its initial state is on the left side of the well, and this is its energy distribution. If I hit animate, you can see we're marching forward and time energy is conserved. Okay, and I sped up the video just for time's sake. Let's also see what happens when we put in energy dissipation now. If I hit animate, you'll see now the system energy falls down, and then the oscillations are damping. It's also nice to see this in the position time space. You can see here's the oscillation that gets damped out. And if I move the cursor, it shows you where we're at in this multi-purpose figure. Okay, so then under options you can enable the advanced menu, and then with the advanced menu you can make a movie of it. You can just show the energy plot. What else can you show here? Yeah, so basically we can plot whatever's in that multi-function plot. So let's try that. Okay, and then if I wanted to make a movie, well, you can just click this button and it will make a movie as an AVI. And let's see, what else do we have? Okay, so you can reuse new figures. Here's this figure. If I click reuse, let's see how well that works. Oh, that's a bug I guess I'm going to have to fix. But nonetheless, you get the basic idea for this GUI. I'll probably fix that later. Thanks for watching. If you liked the video, please feel free to like it and subscribe to the channel. Share the video. Thanks for your time. Have a great day.